enforcement of wideband line model through perturbation of residues and poles. Andre, you have to project the presentation, which is recorded. So the presenter is Ilhan Kocar. Ilhan Kocar is a full professor at Polytechnique Montreal. He received a PhD degree from Polytechnique in 2019. Ilhan's career highlights include contributions to professional simulation tools and development of solutions for large-scale integration of inverter-based resources. He has performed many grid consulting projects that cover design, modeling, analysis, and validation of field measurements. His research is on the development of concepts, models, and methods for analysis of power systems in a wide spectrum and large-scale integration of power electronics-based systems into grids. Please, we can start the video.
Welcome to this presentation of our paper. The title is Passivity Enforcement of Wideband Line Model through Coupled Perturbation of Residues and Poles. I will be presenting you the paper today. My name is Ilhan Kocar and I'm a professor at Polytechnique Montreal. First, a brief introduction. Frequency-dependent line and cable models, such as universal line model and frequency-dependent cable model, represent characteristic admittance and propagation matrix functions in the form of rational functions. This provides efficient simulations in time domain through recursive convolution schemes. However, rational fitting algorithms do not guarantee passive models. As of today, there is no method that enforces passivity at the fitting stage. A model is deemed passive if its line admittance matrix equivalent is positive real. The line admittance matrix equivalent means the admittance matrix that we obtain using the fitted characteristic admittance and propagation function. Violation of passivity may lead to unstable simulations in time domain. These manifest in the form of numerical explosions. So what happens if a wideband line model is not passive? The current approach is to enforce passivity by altering the matrix of residues of either the propagation matrix or characteristic admittance. Note that passivity violation is due to fitting errors, and particularly encountered in the fitting of H, but the line admittance is a function of both YC and H. So although not guaranteed, it is possible to achieve passivity enforcement by perturbing only the residues of YC. Another point is to keep in mind that residue perturbation causes a deviation in the frequency response of the model and in the line admittance matrix. This deviation must be minimized to preserve the accuracy of the model. We should meet the fitting tolerance criterion even after the perturbation. Finally, we can group the previous works in three categories. First category is the perturbation of residues of the characteristic admittance. This is implementation-wise straightforward since there is a linear relation between line admittance matrix and the residues of characteristic admittance. Second category is the application of external correction terms. This approach has the highest risk of accuracy loss. Finally, the perturbation of the residues of propagation matrix is mentioned in the literature, but the relation between the residues of H and the admittance matrix is nonlinear, and there is no clear formulation in the literature to cite. So why do we see only residue perturbation in the literature, and not, for example, perturbation of poles? This is likely caused by the easiness of formulating the induced deviation as a function of the controllability gradient. This is only possible for perturbation of the matrices of residues. Another argument in favor of residue perturbation is that much effort is invested in finding the natural frequencies of any system, or poles, and hence they should be left intact. In this paper, we explore and present the advantages and limitations of perturbing all elements of the characteristic admittance, not only residues, but also poles and constant term. We propose to define the induced deviation in terms of the relative error and Frobenius distance between systems for accuracy preservation. Before going further, I would like to go through the basic equations related to nodal admittance, propagation function, characteristic admittance, and passivity condition. The propagation function is fitted using this function here on the left. It is composed of delay groups and a set of poles for each delay group and residue matrices. The number of delay groups is equal to or less than the number of conductors. This is because some delays are very close or repetitive, so we group them. For each delay group, I have a common set of poles, and for each pole and for each entry of H, I have a residue. Therefore, I have here residue matrices. The size is equal to NC by NC, given that NC is the number of conductors. The characteristic admittance is fitted using this function here. I have a common set of poles for the characteristic admittance. And for each pole and for each entry of YC, I have a residue. Therefore, I see again here a residue matrix with a dimension of NC by NC. And I have a matrix here consisting of constant terms. The nodal admittance matrix can be generated using the fitted H and YC, and this nodal admittance matrix should be passive. The passivity condition here is done through the theta function of Yn. Theta function here is the sum of Yn with its Hermitian. All the eigenvalues of this function should be larger than 0 for all frequency samples. When we do frequency sweep to test the passivity of Yn, we should make sure that we have a fine sampling and we don't miss any sample. An alternative would be use of the Hamiltonian test, which of course shows all the passivity violations. However, it scales poorly with the increasing number of orders. Therefore, because of its robustness, we use the frequency sweeping technique to understand if there's a passivity violation or not. Here, another step before applying the passivity enforcement is the similarity transformation. In order to reduce the size of the matrices involved in passivity verification, we apply a similarity transformation, which is given with the matrix here, J. And the final matrix that I obtained by applying this similarity transformation is Yj. And I'm checking the eigenvalues of Yj in order to reduce the size of the matrices involved in passivity verification. So this is the final passivity condition that I would like to check, and I would like to make sure that my matrix is passive and my model is passive. In this slide, we can see the proposed formulation. The equation here represents the proposed formulation, which is a linear approximation of the passivity condition. I have perturbations in vector form for residues, poles, and constant term, such that it makes all the eigenvalues of the Yj function on the positive side. The relation between the eigenvalues of the theta function of Yj and the perturbations in residues, poles, and constant term is nonlinear. Therefore, I am here proposing a linear approximation which uses the first differential of the eigenvalue function. If I had only perturbations in residues, I wouldn't need such a linear approximation because the formulation would be linear already. This is what we see in the conventional literature. However, in this paper, we want to explore, present, and understand what happens if we perturbate all these elements. Can we fix cases that cannot be solved with residue perturbation only? Here, you can see the relative perturbations in vector form on the right-hand side. This is the perturbations of residues, poles, and constant term. The details of the first differential of the eigenvalue function are available at the appendix of the paper, so the readers who are willing to implement this technique can find all the details at the appendix. Once I apply this perturbation, I need also metrics to understand the efficiency and to see how much deviation that this perturbation induces. So the resulting deviation is measured by applying the feature selective validation method between DC and 100 MHz with 100 samples per decade. FSV gives a metric named Global Difference Measure, GDM, which yields a low value when the two datasets are in good agreement. In other words, when the deviation is low. Ideally, GDM should be less than 0.1 so that I have an excellent level of similarity. If it is between 0.1 and 0.2, in this case, I have a very good similarity. And if it is between 0.2 0.4, it is still good. Up to 0.8, it is considered fair, and after that point, I should avoid using this perturbation. And I should try something else because I lose my accuracy and the deviation is too much that I cannot meet anymore the fitting tolerance that is requested by the fitter. Here we see the test case that we used to understand the advantages of the proposed method. We have here 3 coaxial cables and we have 2 conductors for each cable. We obtain 5 variations by using this case by varying geometric and electric parameters. Here you can see all the parameters: the resistance of conductors, the soil resistivity, permittivity, insulation loss factor, and also the geometric dimensions. And you see here the length of the cable is different. So we have 5 different test cases. Then we use universal line model or frequency-dependent cable model to obtain our frequency-dependent models or wideband model. Here we can see that the number of poles of characteristic admittance, it varies between 11 and 20. Here I can see the number of groups related to the fitting of propagation function, and it varies between 4 and 6. The number of poles, it goes up to 31. This is the number of poles per group. I only write here the maximum number of poles that I see. And whether I apply DC correction or not to improve the fitting accuracy at low frequencies. I can see the fitting frequency range. It may start from 0.01 Hz and it may go up to 10 MHz or even 100 MHz. And I can see here passivity violations. In all cases, there is a violation of passivity, and I show here only the maximum violations. And this is observed with case number 2, which is equal to minus 1.18, 10 to the power of minus 4. And this is observed at 35.5 Hz. So, I apply 3 different perturbations, either residue perturbation, this is the conventional approach available in the literature, and I also apply combined residue pole perturbations, which is a new method and proposed in this paper. And finally, I also try combined residue, pole, and constant term perturbations. For the 5 different cases, what I see here that with residue perturbation, I can fix case number 1, case number 4, and case number 5. By applying the combined residue pole perturbation, I can also fix case number 2. Then I add constant term perturbation, I can fix all cases. On the right hand side, we see the GDM parameter, so it shows us the level of deviation. And I can see here that when residue perturbation is successful, it results in very good GDM values. Whereas With combined residue pole or residue pole constant term perturbation, sometimes I'm in the fair band. So when it comes to conclusions, perturbing all elements has the best performance in terms of removing passivity violations for the considered cases. However, residue perturbation induces the lowest deviation whenever it is successful. So we recommend perturbing all elements only when residue perturbation fails. Thank you for listening.
Thank you very much for this presentation. Now it's time for questions. Any questions? No questions in the Q&A, no questions in the chat room.
Okay.
Okay, well, I cannot ask any questions. I'm co-author, you know. So perhaps
there was also a slide in the end, a thank you slide for the research funding organizations, such as the chair program, but somehow it didn't appear. Yeah.
It's not it. Okay, so since I don't see any questions in the Q&A, neither in the chat room, I think we can move ahead. So we can move ahead now to the